are called of the list of the sequence. We will refer to them as, so this you can think a definition, are called elements, or sometimes we will say members, or very often we will say terms. So I'm just going to use elements more frequently. So elements and terms, and this is the definition of the sequence, okay? This is actually a definition. Now, formally, so a very simple sequence, let's say 1, 3, 5, 7, etc., is the sequence that contains the odd numbers. So this is sequence. Okay. A series is a sum of elements of a sequence. So this is the definition actually of a series. And again here an example, 1 plus 3 plus 5 plus 7. So here, if you talk about series, you can talk about partial sums or about which means the sum of some elements of the sequence, sorry, or you can also talk about the entire sum, as we will see in the next part of this chapter. But today and for the mock exam, we will care about the sequences. Now, formally, the sequence, you can look at it as a mapping or a function. We talked about functions. So another definition of a sequence, we can look at a sequence as a function with a specific type of domain, is a function that, so a real number, it assigns a real number let's call it an, a sub n, to each number in. You remember we defined we defined the whole numbers, you remember? We said it's the set that contains the natural numbers together with 0. So this one we defined it as, if you remember, as W. So here I use n united with 0, which means a non-negative integer in general. Okay. Now, before I start with that, to avoid any confusion, as always, I tell you differences. Now we will see some formulas for sequences, and maybe if you learn this at high school, you might think, well, this is different than the one I learned there. In sequences, it's important which index you start with. Okay. If you start with 0 index, then you have, of course, a different formula, because if you start at 0, then the fifth element will have the index a sub 4, right? However, if you start at 1, the fifth element will be a 5. Is this clear? It's just like in some countries, I don't know how is it in your country, if you go to a building, walk into a building and you just want to use the elevator, some countries, they have the ground floor, they call it 0. So if you want to get to the 4th floor, then you are pressing 3, right? If they start with the ground floor at 1, then you need to press 4, okay? So it's just indexing that shifts, but at the end of the day, it will refer to the same, okay? So here it's important, if we talk about sequence, you just define, because when we talk about sequence and later about series, the first element plays a very decisive role, okay? So as follows. So we will define the mapping or the function here. This function, it has a domain, as we mentioned, and it maps elements to R. Okay, so it's domain, and each n here is mapped to a sub n. Actually, this is here the explanation. Okay, if I take an element here, so obviously, what are the elements of this set here? This set here, it contains the elements 0, 1, 2, 3, and this is actually an index here. So this is an index. So for instance, if we agree to use n united with 0, then the first element, it will be A0, okay? Second element A1, and so on. Okay, so the elements here, it will be A0, A1, then we have here A2, here somewhere we have AI minus 1, AI plus 1, and so on. Okay, so each AI is called, as we mentioned, a term or element. Of course, I equals 0, 1, and so on. Okay, now you see here, this is a function. This is a function, and one way to generate the elements of the sequence, you know, at the beginning of this lecture, I gave you a sequence and you were guessing, so informally. So you were trying to find a relationship between the successive elements and so on. Now, there are two ways to generate the elements of a sequence. One of them, if we just give the formula for that, right? Okay, maybe can you think of a formula for this one? Sorry, I hope you can see it. The odd numbers here. Can you think about a formula there? Sorry. How will you, if n is 0, how will you generate 1? 0 plus 1. Okay, at 2. N plus 2. Okay, so this is where to generate it. It's just like previous element plus 2, right? Actually, to generate the odd numbers, you just take 2n plus 1, yeah? F of n, 2n plus 1. Then at 0, you will be having 2 times 0 plus 1. At 1, you have 2 plus 1, and so on. Okay, so here an example, you can say, example, 2n plus 1 will generates 1, 3, 5, and so on. Okay, so here at 0, you will be getting 1. If you plug in, so here, important is that you think about a sequence as, let me see, as an index. That means here you have in mind a running index here. So this is at position 0, 1, 2, 3, and so on. So here this is A0, this is A1, this is A2, and so on. While these indices here are n, okay? So A sub 0 is now here, this one is our first element. And again, I warn you here, if you assume that your sequence in some literature, it might be defined that by default the first element is A1. No problem. Then the formula, of course, will differ, right? The formula will look a bit different here. Different because you will be having the, as I told you, a shift of one position. Okay. So I'm sure later when we get to some formulas, I will just remind you with that. Okay. So now, if we generate the formula, if we can write this as a function, then we talk about the so-called explicit. Okay. Let's say formulas for evaluating sequences. So we have two different ways to evaluate sequences. The first one, we say it's an explicit what's this explicit formula. That means you just give it as a function. Okay. So for instance, you say f of n okay. So for each n, you just evaluate f of n. And bear in mind that n is a non-negative integer, f of n is a real number. So this is the first formula, the explicit function. And the second one, which is called the recursive formula. Recursive formula is actually terms are generated using previous terms. A very famous. So now when we talk about sequences, we will see that sometimes you can give the explicit formula as well as the recursive formula for some sequences, but there are sequences that are defined only as the recursive formula. The famous Fibonacci sequence, I think we talked about it with God's number, or the magical number 1.618, I think. We talked about it. You remember when we talked about golden ratio? Yeah? And we said that it is everywhere in nature. Yeah. If you look at a pineapple, a banana, or logo of Apple or any other company, or if you look at trees, for sure this Christmas tree has also this pattern. Also the ratio of between, I don't know, human beings arm distance between the tip of your fingers, and weight and height and all these, and also face, etc. It's called the golden ratio, and this we will talk about it later. Fibonacci sequence. Anyone knows how it originated? Sorry. Well, there's these stories is just like a myth, It's just like I don't know. It's just like Santa Claus, It's just some. There are different, different stories, yeah. But I think this is historically maybe proved that Fibonacci in the Middle Ages, he wanted to find out the number of rabbits, assuming that we start with a pair of rabbits. If we keep them, isolated from the rest of the world, how many rabbits we will have after 1 year. So this was actually the idea, and it became, even though it's very trivial, it became very famous. And then later they saw there's a relationship with the flower, the shape of flower, pineapple, and then if you Google it, you will get crazy. Actually, what this called the ratio. It's everywhere in nature you will find it. So the Fibonacci is defined recursively. That means here, what means recursively? You will assume. So for instance, Fibonacci, it's 0, 1. Then you add the two previous numbers, right? What will come next? 1, 2, 3, 5, 13, and so on. Yeah. Now the golden ratio is actually at some time here. This is the amazing thing about this sequence, that at some stage here you will be getting a constant if you are dividing two successive terms. Yeah. And I heard also there is a golden angle or God's angle. I don't know. It's 137, right? 37. So it means if you divide it by the rest of 360 minus, you will get this golden ratio. So, okay, so this is the definition here is that usually in recursive formula, you need something that we call termination condition, right? So in information technology, in computing, I think if you are working with codes, you might be evaluating, I don't know, factorial here. So you need something that we call, I don't know, the Turing machine code. That means you need a halting, let's say, condition. That means a condition that the algorithm will stop there and delivers a value. So here we assume A0 equals 0, okay? A1 equals 1, and then A2 is just so for n greater equal to 2, it's generated using the two previous terms. So this will generate this sequence, okay? So this means n minus 1. So usually in a sequence, we give a term that is called the general term or the generation term. Okay, and now to distinguish the equality here from definition, I don't know whether this is used in English literature, but in German textbooks, you find it very often. We will be just using this colon ahead of the equality. That means it's defined as, okay? So this here, this notation here, so I just put it here on the side. It means defined. Okay, so it's this colon followed by equality. Okay, so it's defined as whatever comes next. Okay, so here this last sentence here, it says that for any term starting at A2, the second term onwards, you just add the two previous terms, the one to its left and the one to its left. Okay, this is what this sequence is about. I hope you get the difference between the, so for instance, here we got f of n equals, we said 2n plus 1 will generate 1, 3, 5, etc. So explicit means you will use only n to the right. It's a function of n. And recursive formula, it's using the previous terms. Actually, I had here a worksheet today where you find also different ways of generating. I think just a very simple exercise to evaluate the first 5, 6 terms. Yes, please. This one we start with 0 up there, right? We start with 0, then you get 1, right? Yeah. So this is the explicit form. It's just like a function, but here the difference is that our domain here, it's a positive or 0. It's a non-negative integer. So it's not a function from R to R. It's a function from N together with 0 to R. Now the second one, it's recursive. Recursive means you define the current term using previous terms with some formula that's related. As you see here in a recursive formula, you will find A sub something here, okay? While in this one, you just find N. Okay, so recursive, as it's stated here, terms are generated using previous terms. Okay, some formula. I can come here and say it's just 5 times the second term, the previous term times 12. It's the position, right? It's the position. Okay, this one means the term to the immediately to the left of N. This one means it's the one before, so it's two positions before, right? Yeah. So this is the meaning of the recursive, yeah. So this index is just a position, right? It's just a position. Any other questions? Okay, let's see the guys online. They have any questions? Who you can't see? Still, you can't see? Yes. Guys, can you see say something? Now you can see, right? Okay, great.
Yeah, we
Any
can see them.
questions? Okay, now let's turn to some special types of sequences. Now before that, as I mentioned here, we as always we agree about notation, and I tell you that there are lots of notation used in literature, but we will. This A sub n within parentheses, it refers to the sequence. And AN will be defined as it will be given as a formula, whether explicit or recursive. Now, in some literature, you might see something like that. I don't know. I saw with curly parentheses, and then here n equals 0 to infinity or something. You need to stick to what the reference you're using is agreeing on regarding notation. Okay, so sometimes, but we will just use this simple one. So when you enclose it within parentheses, it means the entire sequence, and this is here the general term formula. Okay, whether, as I mentioned, it is explicitly defined or recursively. Okay. Now here A0 will refer to first term if of the sequence. And later we will talk about S sub n or sum of I equals 0 to n of AI. This will refer to the series. We will talk about it later in details. So either we will use S sub, for instance, S sub n, if I want the sum of the first 5 elements, I can write it S sub 5, the sum of the first 5 elements, or I just can write it the sum of I equals 0 to 5 of AI. Okay, so okay, let's take now an example just to show you how to use these notations. Example now 3, 6, 9. You said here 12. Okay, now for the beginning, we will assume that we have the counter here. So n equals 1, 2, 3, and this is A sub n. Okay. Now, what we will give two formulas here. So formula here, an and an. Now here we will give it as explicit and as recursive. I told you in many cases you can give it as both. Okay, who can help me? What will be the formula here that generates this? Yes, please. Yeah. You are not sure about the definition? Yes.
A-N plus A0 or something. It's using the previous, so it's using
A0.
A0 plus A-N.
But recursive, it deals with the previous, right? So you can't have an plus 1 because you don't know it already. So maybe A0. So how would you generate 3 from n? 3, yes? 3n plus 3. You can just take 3 out, right? It will generate it, right? At 0, you will be getting 3. At 2, at 1, sorry, you get 6, right? Or as you call it, say 3n plus 3, right? So if you plug in 0, you get 3. If you plug in 1, you get 6. If you plug in 2, you get 9, and so on, right? Got it? Three times 0 is 0 plus 3, you got 3. N equals 1. 3 times 1 is 3 plus 3, you get 6, and so on. Okay, now here using this formula, if I ask you what is the 15th element, then you will say, this is the thing I told you about. 15th element is n equals 14. Yeah. This is the thing I was telling you about. If you go to the nth floor, you know, it's just if you start with 0, then the 15th element has location n equals 14. If you start at 1, it has location 15. It's the same, but it's just a shift. Yeah. I'm sure in many countries, you might go and you want to go to floor, then it's different from one country to another, right? Sometimes you end up going to the wrong floor if you just assume. Here in Germany, we are in which floor now? Second or first? First, right? First. Some countries, if they consider, you know, here in Germany, they consider it the ground floor, then 1, 2, 3, 4, okay? Then some start with, even they have minus, okay, in the other direction. Now, recursively, what does that mean, recursively? Recursively, you need to, of course, you need, notice that by recursive, this is a very important notice that I know you are studying informatics and programming. Now, in computer science, we have two issues when we develop an algorithm. The first issue is the correctness. That means, is this algorithm going to give an input for each, an output for each input? This is number one. Number two is what we called the termination. Yeah. And that's why, because if you have an endless loop, then I am sure many of you got somehow endless loop where your system crashed or whatever. This is because then you will be ending a loop and you don't have a termination criteria. So here, when you talk about recursive, you need to define the first, the second, you need to define the basic, right? So and always by recursive, think about, I don't know what's its name in Russian. This, these Russian figures, yeah. Matochka, something like that, yeah. So this is recursion, yeah. You have one embedded in the other, and the other, and the other, and the other, yeah. But then you need somewhere to get to the kernel. You need to get some last figure that is not. You can't go further, right? So here, when you talk about recursive, you need some termination point, okay? So recursively, we will say A0. How will you talk about recursive? Anyone can think about it? So recursive, first of all, we will define the first element. Okay. How are starting from here? Okay, the first element we defined it. Then the second element is just the previous plus 3, right? So an minus 1 plus 3. Okay, this means the previous element. Okay, so an a sub n plus 1 plus 3. So this is the formula. Okay. Okay, you see the recursive, the difference. Recursive here, we use here to the right, we use an index of some element. That's why it's recursive. Whether like Fibonacci, you use 2 terms or 3 terms, but you use previous terms to define the current term. I hope it is clear. Okay, there are different types of sequences. Question? Okay, now we will turn to different types of sequences, and the first type is very simple. So I'm going to list 6, 7 types of sequences. So major types of sequences. So what I'm going to do, we will introduce these types, define them maybe explicitly or also, if possible, recursively, and then we will generate the first 4 terms. Okay? So the first type here is the constant sequence. Constant sequence, you just have a number. So an, and again, this is defined as equals C, and C is in R. So C could be any element. So let's list here is sub-0 is C, A1 is C. So if I ask you what is the 100th element of this sequence? C, huh? Okay, so it could be 1, 2, 3, any constant here. Okay, so this is so-called constant sequence. The second type, which is also almost trivial, also identity. So the identity sequence, it will is defined as A sub n. Again, this is definition equal just n. Okay. So A sub 0 is 0. So you see here, the fourth element is A sub 0, 3, sorry, because we started with. Okay, and here, of course, n is natural number, or could be a 0. And again, if we start at 1, so if we define this as 1, then we start at. Now, there are some sequences like the next one where you are forced to start at 1. You can't start at 0. This is the sequence. If you can describe it, so this is definition here. N greater or equal to 1. Okay. Or n is in n. Now here it doesn't make any sense to talk about A0. Now here this you can say is the reciprocal of the identity. It's possible also. Now A1 equals 1 over 1, which is 1. A2 equals 1 over 2. A3 equals 1 over 3. A4 equals 1 over 4. Okay. Now this sequence has a nice feature, is that maybe this is just let's say preparing you to the next concept of some behavior of sequences that also plays a decisive role when it comes to examining the so-called convergence or divergence. Is that, as you see here, 1, then 1/2 is 0.5, right? 1/3 is 0.334, let's say. 1/4 is 0.25. 1 over 5 is 0.2. So as you see here, as we proceed here, n increases, this number decreases. And actually, if you think about it, each element, an, is strictly less than an plus 1. Okay? That means each element, no. Which one is less? An minus 1. Okay? So each element is less than its previous element. Okay? And this terms we will later define it, maybe in the new year, as a so-called decreasing sequence, because each element, or strictly decreasing sequence. Okay, any questions so far? Now this element here, this sequence here at infinity, it will get close to 0 because the denominator will get very, very large. So this is a nice and very important sequence here. Another sequence that is important here, and this is only an example, what we call the alternating sequence. Alternating this is an alternating sequence. So we define the general term as -1 to the power n. Let's say 1 over n. Okay, and here again n is n, that means 1 and so on. So it's not defined for 0. Now, as you see, this sequence, -1 to the power n, that's why it's called alternating. it will deliver a negative. I think it's not clear here somehow, right? You can see it. Okay, guys online, is it clear, the text here? Okay. So you see this alternating, it means at the position 0, what will, sorry, 1, sorry, a sub 1, what is the element here? Just plug 1 for n, negative 1 to the 1, right? Times 1 over 1. This is equal to minus 1 over 1, which is minus 1. Okay? A2 here is negative 1 squared times 1 over 2, right? N. Okay? Notice here that that's why it's called alternating. At the odd position, you will be getting a negative sign. At the even position, you get a positive. So this is in mathematics the way to generate negative 1. Okay? If you want to generate negative 1, 1, negative 1, 1, negative 1, so alternating. That means this will go somewhere to for an odd value in the negative, and then goes to the positive for even, and so on. So that why it's just zigzagging, it just goes up, down, up, down. Okay, A3. What is A3? Minus 1 to the power 3 times 1 over 3. So what is A3? Minus 1/3. A4 minus 1 squared, which will deliver positive 1 over 4, and so on. Okay, so this is an alternating sequence. Now we come to something that might cause confusion. So that's why I will give you both definitions. I don't know, anyone studies arithmetic and geometric sequences at school? Yes? So okay, so what's wrong with this? Okay, the alternating sequence, it will deliver negative for the odd value because you have negative 1 to an odd power, and for the positive for the even. Now we have two types of sequences that are very important for this section, and also for the so-called arithmetic sequence. The arithmetic sequence. Now here, given A0 and so given usually the first element and a constant D, and AN is defined as, now here I will give you this formula. Yeah, maybe I just write it the other way around. A0 plus N times D. Okay. So the given usually the first element and a constant D, and each further element is just generated. On focus. Okay, each further element is just generating by adding n times this d to the previous element or to the first element. Okay, so if you want, this is the explicit form. This is the explicit. This one is explicit. Now, how to generate the elements of this sequence? So A0 is equal A0, of course. A1 equals to A0 plus n times d, so plus d. A2 equals A0 plus 2d, right? But this is equal to A1 plus d, because A0 plus 1d, it's A1. Okay? A3 equals to A0, according to the formula, n is 3, so 3d. And this is equal to A2 plus d. So always when you move further, you add d, okay? You add d. So that's why this particular formula is used for if someone is investing money in account with some, let's say, interest rate with the so-called simple interest formula. So each year you will be getting d, which is the amount times the interest rate, which is constant each time. Okay, I think you have some exercise for today using this. Okay, so now explicitly we defined it, how we can generate this recursive formula for this. As you see here, look at this one. It's just this A2, A1 plus D. So each element AN, of course, A0 equals to 3, so A0 equal to D to A0. Then you have AN equals AN minus 1 plus D. Okay, you see here, you just, each element, you add D to the previous element. And always think about that as the, if as I mentioned, the so-called simple interest rate formula. So for instance, if you are just having an account with 1,000 euro at 2%, then each year you will be getting, I don't know, what is 2% times 1,000 is 20, right? So after next year you get 20. 3 years you get 20 times 3. 5 years you get, each year you will be adding this sum, in this case is D. Okay. Of course, here you can write it also as AN plus 1 equals AN plus D. So it means just the previous element, add D to it, and you are there. Okay, so this is the so-called arithmetic sequence. And this is the simple interest rate formula is also same. Simple interest rate. So we will talk more about it during the tutorial. Now, another sequence that is also related to some interest rate formula, but it's a little bit more realistic, is the so-called the geometric sequence. And this is number 5, I think. Okay, geometric sequence. Thank you. Geometric sequence is, again, here you are given A0 and some real number, which is Q. Now this Q here is called the ratio. Now A0 equals A0, of course. A1 equals A0 times Q. Let's say here Q to the power 1, which is Q, of course. A2 equals A0 times Q squared. A3 equals A0 times Q cube, and so on. Okay, so in general, you have here AN equals A0 times Q to the power N. Now here I admit that maybe I forget also when we talked about the other sequence. Now, maybe in some literature, someone here told me you studied that before, right? What was the formula for arithmetic sequence did you study? An minus 1? The same. Yeah. What about the explicit formula? It's n times d or n minus 1 times d. Yeah. So I hope it's clear for everyone. If you just shift, that means here we started at A0. Now if you start at A1 here, then the nth will be n minus 1. So you will be shifting. Okay. So here if we start at if we start at 0, okay. Now if we start at 1, then the formula here an equals A1 times Q to the power n minus 1. Okay, you got the difference here? Of course, and here also the same. Let me just go back to this one, and because some students from previous experience, they just say, okay, so this is, where is it? This formula here, if we start at, okay, so A1 equals A1, of course, then AN equals n minus 1 AN equals A0 plus n minus 1 times d. So here, if we start by, okay, so here if we start at n equals 0. Okay, that means if the first element you are given, it has the subscript 0, then you rather use this formula. If it is 1, then you use this formula. So sometimes it is confusing, but if you think about it, it's just a shift, right? It's just a shift. So here, if we just start numbering these rows here in this classroom, this is row number 0, then the fifth one will be labeled number 4, right? If I start here at this is the first one, the fifth one will be labeled 5. It's just labeling, okay? But be careful to this point. Now the thing here is that the recursive formula, it doesn't affect, it's not affected. Now as you see here, let me just go back to these elements here. So this one here, it is A0 times Q times Q. But this A0 times Q, it's A1. So it's A1 times Q, right? This one here, it's A0 times Q squared times Q. So it's A2 times Q. Okay? So recursive formula for this, it's Q equals, if you just take this one, AN divided by the previous. That means two successive terms, the successive terms divided by the previous term is always a constant, is always a constant. This is the recursive. And that's why this Q is called the ratio. And this formula, it's actually in financing is called, this is used to calculate the so-called the compound interest. Compound interest in financing. The difference is between the compound interest, as you see here, you just imagine you are investing again 10,000 euros at 2% for 5 years. So well, how you call this starting capital principal, I think it's called, right? The amount of you invest at the beginning. After 1 year, it will be added to it the interest of the first year. Okay. So the second year, it will be, the interest will be given for the principal plus the amount of interest that was added to the account. That's why it's called compound. Okay. Call it in German, Zins or something like that. The interest of the interest, right? Sorry. Okay, now the other thing is that we'll take some example. Is this one? Okay, we mentioned actually the Fibonacci sequence. The Fibonacci sequence and the amazing number. So A0 equals 0, A1 equals 1, and AN equals, all defined here. AN equals AN minus 1 plus AN minus 2 for N greater or equal to 2. Okay. And we said that we have A0, A1, A0 equals 0, A1 equals 1, A2 equals 1, A3 equals 2, A4 equals 3, and so on. Actually, for rabbits, you need to start at A2, right? Because otherwise, you will be terminating from 0, right? But this is the general formula. Now this one here, this one is actually somewhere here, this the you will be getting a golden ratio. So an minus 1, it means here in other words the sum of the two previous terms, right? This is the definition of the Fibonacci sequence. I define two terms and then the rest is generated always by adding immediately the two terms previous to the number, right? The golden ratio is defined as an plus 1 over an. Now I don't know, 3 over 2. Now there is a formula. I just I really don't it's a little bit too complicated, but I think I gave you this number. Let me check. I don't know whether I have it here somewhere. What is as I told you, the golden ratio, it's also called phi. It's 1.618 roughly. And I read that 2022 that someone, I don't know to how many digits, wrote this one. It is in any way a so-called non-rational, not rational number. The golden angle is 173.5. Why? Because 360 minus 137.5, okay? Then you will be having 222.5. You subtract it from 360. If you divide 222 by 0.5 by 137.5, you will be getting the golden ratio. Okay, there is the so-called binets. Binet is scientific. There is a formula, binet formula for if you want, you can Google it, for evaluating the nth term. It has to do with the square root of 5 and n minus 1. You can Google it, Binet's formula. Let me check how they write it. Binet, yeah. Binet's formula will give you. So as you see here, if you have a formula for evaluating the terms of the sequence using the recursive formula, it's difficult to look ahead at, for instance, with this formula, it's just like we go back to this, what is it called, this Russian thing? Matuchka? Okay, imagine you are at some location there and you want to go to the 5, let's say, figures deeper, right? You can't jump inside and go to the 5th figure before, right? You need to unwrap it one by one, right? Until you get to, and this is here the same. For instance, with this formula, you can't evaluate the 100th element, yeah? The element at position 100. Because then immediately, then you need to evaluate up to A99, and then you add to it A98, then you have A100, right? But this Binet's formula will give you the solution for that because of this magical number, golden ratio. I don't know. I told you a lot about it. You can Google it and you will be surprised where it has to do with the spiral, right? Spiral. Once I read also the ear, you know, the design of the human ear and flowers, pineapples, leaves, whatever. Yeah? Okay, so golden ratio is related to this very closely. Now, actually, I didn't want to get in this convergence, divergence issue. I just want to leave it after the break, so that's why. Uh, so I will repeat it after we come back. But in general, I will just give you some idea about convergent okay. We will do this again after holidays. But what is meant with convergent and divergent sequences? Now, if I have a sequence, so I have A0, A1, A2, then I don't know, at somehow here I have a counter, right? So here I have 0, 1, 2, someone here I have I, someone here I have N. Now, the topic of studying the convergent or divergent of a sequence, now this is all informal, okay? Informal. I don't want to bother you now before the holidays with this epsilon sigma definition. Now, imagine you have here at infinity. Infinity means I have a very large number, and very large number is something that is, how you call it? It's just not defined. It's undefined, but I'm going to study the behavior of the sequence when n becomes very, very, very large. Now we have two cases. Either the sequence will be approaching some number, in this case, some constant number, we call it a converging sequence. Or it will just go wild, very, very large, or somewhere where it has no pattern of approaching a number, and this is what we call divergent. Okay? Convergent, divergent. Okay? Imagine if you are traveling in a boat in the ocean, right? How you call it? Seagull boat. Anyway, and then you are heading nowhere, or you are heading to some specific harbor. So if you are heading to some constant number, this is what we call converging sequence. Now here for now, I want you to think about 1 over n. We said that 1 over n, it started with 1, right? 1/2, 1/3. Now, when n becomes an infinity, so I am not allowed to use that, but when n becomes infinity, this ratio here, it has 1 over a very large number. It has 1 over a very large number, and it will be approaching 0. Actually, if you take, I don't know, 1 over 1,999, or which year we are now? 20. We are 2043. Okay. Okay, because you guessed it. You have calculator, can you evaluate 1 over 2024, let's say, okay? 24, 1 over 2024. You see, so it's 0.0049, okay? Almost. Huh? Okay, you know how to implement this -4, 10 to the power -4, it means just 4. So that means here, if n becomes, sorry, if n becomes very large, we will get a number very close to 0, right? If you, I don't know, if you just try 1/9,999, okay? Or, you see, oh, this looks good, yeah? So we have 0.001, okay? It's just 1/10 of one, no, 100th of a thousand. Okay? So that means here, this one here, it gets close to 0, as n gets close to infinity. This concept is what we call the concept of the limit. Okay, we will say the limit of this sequence an, if n approaches infinity, is equal to 0. Of course, if this is an equals to 1/n. Okay, so the concept of the limit, so it's just reads the limit of an when n approaches infinity is equal to 0. And now this equal, I will put 100 quotation marks here. Now, even though when we talk about limits, we write equality, but it means it's approaching, okay? So please think about limit. It's approaching. I actually, if you are used to real analysis, you know the function 1/x. If you just plot it, even though it has nothing to do with this course, because it's not real analysis, but nevertheless we will need it for the next course. 1/x, it will be something like that. So it will not touch this axis, so it will not go to 0. And also from this side. That means here it approaches. It's not, it's just like, I don't know, if you go to the ocean, you are on the beach, so you are approaching the ocean, right? You are not in or the sea. So approaching is the concept here. However, we will use equal to, okay? So now the concept of this limit, we will talk later about such sequences. But basically, if you have any sequence where the denominator gets large at infinity, it will be approaching 0. So here, for instance, if you have an equals 1/n squared, or an equals 1/3n to the power 3, this is all going to approach 0. Okay, so whenever the denominator becomes larger, the limit will be 0. Now, after the break, we will look at some properties of these limits. And notice that here in this course, we are talking only about limits at infinity. Next course, we will talk about limits approaching any number, because here we are only using the limits to examine the behavior of sequences at infinity. However, in the second course, we will be looking for real analysis. So that's why here it's not n, it's not a natural positive number, it is rather a generally for all real numbers. Okay, so but for now we will talk about this one. So we will learn how to evaluate some limits at infinity. In particular, if we talk about quotients of polynomials, we will see 3 cases there. So let's take a break for 15 minutes and then we will continue. Oh, by the way,